The concept of vector space was first introduced by the German mathematician Hermann Grassmann in his 1844 work, Die Linear Ausdehnungslehre, which translates to The Theory of Linear Extension. Grassmann's work laid the foundation for the study of vector spaces, a fundamental concept in linear algebra. Linear algebra is a branch of mathematics that focuses on vectors, vector spaces, linear transformations, and systems of linear equations. It provides essential tools for representing and analyzing geometric objects using algebra. This subject is crucial in various fields such as physics, computer science, engineering, economics, and data science, forming the backbone of modern fields like machine learning, graphics, and optimization. This video series aims to teach the basic concepts of linear algebra to engineering students. In linear algebra, a linear combination of vectors is an expression constructed from a set of terms by multiplying each term by a constant and adding the results. A set of vectors alpha1, alpha2 and alpha n in a vector space is linearly independent if the only solution to the linear combination is the trivial solution, where all coefficients are 0. If there exists a non-trivial solution, the vectors are linearly dependent. Understanding these concepts is crucial for analyzing vector spaces. To determine if a set of vectors is linearly independent or dependent, we can use two methods. The first method involves using definition, and the other method involves forming a matrix with vectors as columns, or rows, and checking the rank. If the rank is less than the number of vectors, they are linearly dependent. This method works for both row and column vectors. Let's explore an example to illustrate this process. Let us put linear combination of alpha1, alpha2 and alpha3 to 0. Simplifying and then solving, we get all coefficients equal to 0. Hence, alpha1, alpha2, alpha3 are linearly independent. Another method to check vector independence involves forming a matrix with vectors as columns. Here, the value of the determinant of matrix A is not equal to 0. Therefore, the rank of the matrix is 3, which is equal to the number of vectors, hence the vectors alpha1, alpha2, alpha3 are linearly independent. Note that if we need to find a linear relationship between the vectors, then we have to follow the method first. In the next example, we have expressed the vector 1, 2, 3 as a linear combination of the vectors 1, 0, 0, 0, 1, 0 and 0, 0, 1. Linear span. Let V, F, be a vector space and S be any non-empty subset of V, then the linear span of S is the set of all linear combinations of finite sets of elements of S and is denoted by L, S. Remember the following points first. The span is the smallest subspace of V that contains all the vectors in S. Second, in R cubed if S equals 1, 0, 0, then linear span of S will consist all points on x-axis. Third, in R cubed if S equals 1, 0, 0 and 0, 1, 0, the linear span of S will consist all point in xy plane. Fourth, every non-empty subset of a linearly independent set of vectors is also Li. Fifth, a set of vectors which contains at least one zero vector is always LD. Bases. A subset S of a vector space V is set to a basis of V if S consists of linearly independent vectors. Linear span of S equals V, that is S generates V, that is each vector in V can be expressed as a linear combination of a finite number of elements of S. Finite dimensional vector space. The vector space V is said to be a finite dimensional if there exists a finite subset S of V such that V equals linear span of S. Remember, 1. There exists a basis for every finite dimensional vector space. 2. Any two bases of a finite dimensional vector space has same number of elements. Dimension of finite dimensional vector space. The number of elements in any basis of a finite dimensional vector space V is called the dimension of V. Remember, if V is a finite dimensional vector space of dimension n, then any set of n linearly independent vectors in V forms a basis of V. To illustrate the concept of basis and dimension, consider a set of vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 in S that form a basis for a vector space R cubed. It is easy to check that S is Li using matrix method. Further, any arbitrary element of R cubed can be expressed a linear combination of the vectors of S, therefore the linear span of S is R cubed. Both conclusion implies that the set S is a basis of R cubed and the dimension of the space is C3. Let's explore an example involving the vector space of all 2 by 2 matrices over the field R. We will find the basis of this space and prove that it has a dimension of 4. Let alpha, beta, gamma, and delta be 4 elements of V using elementary calculation. we can check that the set S, consisting of alpha, beta, gamma and delta, is Li and the linear span of S is V. Obviously dimension of V is 4. Thank you very much.